I'm going to present our paper published at the International Conference on Automated Software Engineering 2022. The paper is titled Compressing Pre-trained Models of Code into 3 Megabytes. I'm Joe Young, a PhD student from Singapore Management University. This is a collaborative work done by Jack, Bowen, Hongjing, and David at SMU. Inspired by the success of large pre-trained models on natural languages, a series of pre-trained models of code are emerging to tackle software engineering tasks. For example, researchers from Microsoft proposed CodeBERT and GraphCodeBERT. Researchers from Salesforce design and implement CodeT5. They have been published in good venues like ACL, ICML, and Extra. These pre-trained models of code have achieved good performance on various tasks. Researchers at Microsoft proposed CodeXGLUE, a machine learning benchmark dataset for code understanding and generation. The benchmark categorized tasks into 4 types. For example, a text code tasks include natural language code search and code generation. The code-to-code tasks have clone detection, defect prediction, which are the main focus of our paper. The code-to-text tasks is mainly about code summarization. And a classic text-to-text task is document translation. In ASE this year, we also introduced another task about Stack Overflow answer summarization. So please check it out if you are interested in text-to-text tasks. Although large pre-trained models of code have delivered significant advancement in various code processing tasks, it comes with a huge size and great computational cost, which to some extent prevents the powerful models from being widely used in developers' daily workflow. The figure in the top half is from a survey paper of pre-trained natural language models. It shows that these model sizes have been increasing. In the bottom half, we make a simple timeline of the pre-trained models of code. While this timeline is far away from comprehensive, especially considering that the new models are being proposed. The red dotted lines means that a model of code and a model of natural language share the same architecture and as a result have similar sizes. So from the figure and the timeline, we can observe that the pre-trained models of code are getting larger and larger as well. The large sizes of pre-trained models hurdle their usage in practice. These models consume hundreds of megabytes of memory and run slowly on personal devices, which cause some problems in model deployment and greatly degrades the user experience. We quoted the opinion of researchers at Microsoft. In a paper published at MSR 2021, it says that a 50 megabytes model is a reasonable outbound size for a plugin in a modern IDE or an editor. However, even CodeBERT, which is relatively small, is still larger than 400 megabytes. Such a large size cannot satisfy the desired size requirements. They also mentioned that a 3 megabytes model can be deployed in even severely restricted environments, for example, low-ended hardware used to teach students to code. The goal of our study is to compress the pre-trained models into only 3 megabytes, while maintaining their original performance as much as possible. Let's first briefly discuss the common methods to reduce model sizes. The first one is model pruning, which has 2 operations. The one is to set some parameters as 0 so that there are fewer parameters to be saved, and consequently, the model has smaller sizes. The other operation is to remove some architectural components or parameters. For example, this table represents 3 layers in a network. And model pruning can directly remove one layer to obtain a model with smaller size. However, both 2 operations cannot effectively compress the pre-trained models of code, as they have to keep an embedding table of around 150 megabytes. The method is called model quantization. The main idea is to use lower bit fixed point numbers to replace the higher bit float point parameters. For example, in this table, the first element is a float number of 0.132. After model quantization, we can convert it into an 8-bit integer, which is 0. Typically, the maximal compression ratio of model quantization is 32 times. In other words, we convert all these 32-bit float point numbers into a 1-bit binary integer. The model quantization cannot bring faster inference speed and it usually requires optimized libraries. Anyway, both model pruning and quantization cannot effectively compress pretrained models of code. In this paper, we use another model compression method called knowledge distillation. We can understand it as a process that a student learns knowledge from a teacher. Assuming that we have some input data, we view the large model to be compressed as a teacher. We use the data to query the teacher and obtain the teacher's instruction. Similarly, we send the same input to the student model, which is a tiny model. The outputs from this tiny model are called the student answer. Clearly, there will be a difference between the student answer and the teacher's instruction. So we compute the loss between the two outputs and use the backpropagation to update parameters of the tiny student model. The advantage of knowledge distillation is that the compressed model size is decided by the student model only. So the hyperparameters related to the model sizes can be adjusted in a more flexible way. For example, using a much smaller vocabulary size rather than following the original Colbert model. Well, of course, there's no free lunch. Researchers typically think that there will be a trade-off between the student model size and its performance. So the main question our paper tries to address is that how can we automatically design an appropriate student model that is small enough but is still capable of learning sufficient knowledge from the teacher model? It is non-trivial to find such small models. There are two main challenges. First, the search space for finding appropriate models is extremely huge. Modern models can consist of different architectures and components like LSTM, CNN, transformers, and so on. And each component has some parameters that can be tuned to affect the model sizes, for example, the depth of layers. To tackle this challenge, our solution is to leverage the excellent architecture design of the existing pretrained models instead of searching for a model from scratch. The other challenge is that even if we constrain the search space, we cannot train and evaluate the performance of each candidate model we find in the search process. It will take too much time and computational resources. From the previous literature, some evidence shows that the model performance is correlated with the computational cost of a model. So our solution to this challenge is to use the computational cost, which can be computed statically and easily, as a predictive metric of the model performance. We combine the two solutions together and use a genetic algorithm to search for models that can maximize computational cost while minimizing the model sizes. We call our approach compressor, and here's the overview of our methodology. First, we have a large pretrained model for compression. It goes through a model simplification process where we use a genetic algorithm to obtain a small model. Then we use unlabeled inputs to query both pretrained models and the small models to let the small student model can distill knowledge from the bigger teacher model. Let's look into the details of the model simplification process. According to previous works on compressing natural languages, a tiny model with architecture similar to the large model has performance close to the larger model as well. So we let the small model use the same architecture as the pretrained models, but it uses different hyperparameters. This table lists 5 adjustable hyperparameters, including the number of layers, the dimension of layers, the number of attention heads, the dimension of feedforward network, and the vocabulary size. We use the original hyperparameter setting as the upper bound of the search space to find the candidate models. The first step in using genetic algorithm is to represent solutions as chromosomes. We can use a simple 5-dimensional vector to represent the solution. Each element is a hyperparameter as we discussed in the previous slide. The fitness function consists of 2 parts. On the one hand, we try to optimize the computational cost, which is the G-flops. On the other hand, we try to minimize the model sizes. We use 2 operations to generate new solutions. The first one is a crossover operation. Assuming that we have 2 solutions and we label them using different colors, the crossover operation first randomly selects a position to cut the chromosomes, and then swaps the first half of the 2 chromosomes to generate new solutions. The other operation is a mutation operation. We take one chromosome generated in the previous step, Then we randomly select a position. For example, the third position, parameter A, is chosen. The number 8 is randomly changed to 9 to generate a new chromosome. After generating the new solutions, we evaluate their fitness function and only keep the solutions with the highest fitness function values. We use unlabeled inputs to query models and do knowledge distillation. On the one hand, unlabeled data can be easily collected from open source projects. On the other hand, a realistic scenario is that the deployed tiny model needs to be trained with newly generated data by the users to harden performance, which is typically unlabeled. To train the student model, we don't use a conventional cross-entropy loss. Instead, we use a knowledge distillation loss function proposed in the previous studies. In this formula, Pi and Qi are the outputs from the teacher and the student model. The T is a parameter to soften the softmax function. We evaluate our method on 2 critical tasks and 2 popular pre-trained models. The vulnerability prediction task aims to predict whether a given code snippet contains vulnerabilities or not. The clone detection task aims to check whether 2 given code snippets are clones. We obtain the datasets and the pre-trained models from PyroWorks. This table displays the results of 2 models on different tasks. In the first research question, we explore the performance of the compressed models. From the existing literature, we choose a baseline that can compress pre-trained models most. But it can only compress model code into 7.5 megabytes, still over 2 times larger than what our method can do. We can see that the compressor can better maintain the model performance than the baseline. Compared to the baseline, models obtained by compressor have around 50% less performance job on the clone detection task and around 90% less performance job on the clone detection task. The second RQ cares about the efficiency of the compressor models. We can find that compressor also make model run more efficiently. On the 2 tasks, the average inference latency of the compressed models drops by over 60%. We also evaluate the efficiency of compressor itself. If it takes a very long time to find small models, it may diminish the value of it. Basically, to find the small models, compressor takes only around 30% of the time used to fine-tuning a large pre-trained models on the same dataset, which is an acceptable time cost. Let's discuss a bit how the model size affects the model performance. Generally speaking, if we are more tolerant of model size, we can achieve better performance on both 2 tasks and models. So more performance can be preserved by sacrificing compression ratios. In the future, we plan to support more types of architectures beyond BERT-like models, where we also explore more tasks, more different requirements of compressed models like robustness and fairness. We also plan to mine good design patterns of the tiny models from the open source software. In summary, our approach compressed pre-trained models from 476 megabytes to only 3 megabytes, which is over 106 times smaller. Our approach also reduces the average inference latency from 1.5 seconds per example to only 0.35 seconds per example, which is over 4 times faster. Besides, the models preserve over 97% of performance of the large models. Hope it inspires, and questions are welcome.